Hello and welcome back to Advanced Hydrogeology. Today we're going to be continuing our discussion of finite differences, and we're going to be expanding on the simple finite difference equation that we derived for the one-dimensional groundwater flow equation. So today we're going to be talking about groundwater flow or finite differences for a more complicated system. So this is the finite difference equations that ModFlow uses. And ModFlow is, if you don't know it already, is is the most used groundwater flow model in the world. It was written and is maintained by the USGS. So we're going to delve a little bit into the kind of finite difference equations that ModFlow uses. And these are finite differences for a variably spaced grid and for a heterogeneous three-dimensional confined aquifer. Okay, so let's have I'm gonna share my screen here. And let's remember that finite differences, first of all, let's recall our groundwater flow equation. So recall our three-dimensional heterogeneous anisotropic transient confined aquifer equation. All right, so it's transient. So we have SS dH dt. All right, it's heterogeneous. So our hydraulic conductivity varies with space. It's anisotropic. So we have a hydraulic conductivity specific to the travel in the x direction. And it's 3D. So we have this for each direction. All right. So this is our three-dimensional heterogeneous anisotropic transient confined aquifer equation. And we're going to look at developing a finite differences solution for this equation. All right, and we're going to think about, first of all, a grid So let's just look in the x direction. All right, and let's say that we had a grid. There's one cell. Here's two cells. And here's three cells. And the important thing, so this would be x I minus 1, x sub I, and x sub I plus 1. All right, and the spacing between these is different. So we're going to call this spacing delta x I minus 1/2. All right, because this is the spacing between these two. So this distance here between these two would be delta x I plus 1/2. All right, and then the cell spacing here between the two midpoints, we're going to call delta x sub I. Okay, so let's just remember a few things. So first of all, let's talk about the head, the change in head in time, and let's talk about the first finite difference operator. All right, so remember that dh dt we approximate as h I, and because I'm in 3 dimensions, I'm going to have 3 subscripts, I, j, k for x, y, z here. And I'm going to use n for time at the top. So minus h, I, j, k, n over delta t. All right. So here, where n is my time step, and I, j, k are my x, y, and z indices. All right. Okay, so this equation here is my first operator, right? It's the step here because we're interested in time. It's the future step minus the present step over the change in time, all for some location x, y, and z, or I, j, and k. All right. Okay. So now so this is our left-hand side of the equation here. Now let's focus in on this guy, so this gives us, we can write our left-hand side as SS times H, I, J, K, N plus 1 minus H, I, J, K, N over delta T. And that is equal to the left-hand side of our equation, or approximately equal to SS dH dt. Okay, so now let's talk about this guy d dx of k sub x dh dx. And let's remember that we can think of this as the finite difference operator dx of the finite difference operator of h. All right. So if we do that, we can write this first term, d dx of k sub x dh dx equal or approximated by 1 over delta x I j k. All right, so if I scroll back up here, delta x I j k would be this, our cell spacing here, delta x sub I. This would be our cell spacing, delta x sub I j k. All right. This is not equals. Here, so give me a sec. Okay. Times the first one of these, k sub x I plus 1/2 j k. So this is the hydraulic conductivity here, or the average hydraulic conductivity of the I plus the I plus 1 cells. All right, so it's this upstream average hydraulic conductivity times, we're going to do the finite difference operator of dH dx here. All right, and it's going to be the upstream one. So we're going to be looking at the difference in heads between these two nodes. So this will be h n plus 1 h sub I plus 1 j k. So we're just looking at the difference in the x direction. So just this first indice for x is increased. These other two are staying the same. Okay, minus h I j k n plus 1. And I'm doing these at the n plus 1 because I'm doing this for the implicit method, where we're going to end up solving this set of equations for the present using the future. Okay, and this is over delta x I plus 1/2 j k. All right, so that's the first term in this difference. And now I need to subtract the second term. So this is all still within these brackets. Minus k sub x I minus 1/2 j, k times h, I, j, k, n plus 1 minus h, I minus 1, j, k, n plus 1 over delta x, I minus 1/2, j, k. All right, so this is this first term. It is, I should erase this squared here. Doesn't make any sense, sorry. D dx of k sub x dh dx. So we have the first, the upstream one, minus the downstream one. And then we take d dx of h of x, that's these parentheses here. So we have the upstream minus the present. And then here we have the current location minus the previous location. All right. And that is the term for the finite difference form of this term. All right. And it turns out you can do this for each one of these directions here. All right. So we just wrote it out for the x direction. We can do it for the y and the z. So I'll write it for the y here. So d dy k sub y dh dy can be approximated by 1 over delta y I j k times parentheses k sub y I j plus 1/2 k, because now we're looking in the y direction. All right, so all of our indices are going to be here in the j, or all of our changes in indices, h, I, j plus 1, k, minus h, I, j, k, and these are all at the n plus 1 time step, over delta y, I, j plus 1/2 k. All right, so now this would be the spacing in the y direction, advanced or just greater in y. Okay, minus k sub y I j minus 1/2 k h I j k n plus 1 minus h I j minus 1 k n plus 1 all over delta y I j minus 1/2 k. Okay. And finally, for the z, d dz kz dh dz can be written, same template. We're just going to be using delta z now. And instead of, and now the indice that we will be looking at is this guy in the k. So this would be kz ij k plus 1/2 times h I j k plus 1 n plus 1 h I j k all over delta z I j k plus 1/2. All right, minus k z I j k minus 1/2 h n plus 1 I j k minus h n plus 1 I j k minus 1/2 over delta z I j k minus 1/2. Shoot. Okay. So now we've got all three of these, and we can set our equation as this side here is equal to this guy. Let's name them. So this one is 1. We'll call this one 2. And we'll call this one 3. And this one 4. All right, so we have 4 terms, and we can write them all out. We can write them all out here. So here's our full equation is 1 is equal to 2 plus 3 plus 4. All right, so we have SS H n plus 1 I j k minus h I j k n over delta t is equal to 1 over delta x I j k k sub x I plus 1/2 j k h I plus 1 j k minus h I j k n plus 1 n plus 1 over delta x I plus 1/2 j k minus k sub x I minus minus 1/2 j k h I j k n plus 1 minus h I minus 1 j k to the n plus 1 over delta x I minus 1/2 j k. All right, that's term 1 or 2. Okay, plus the y direction one, so 1 over delta y I j k k I j plus 1/2 k h I j plus 1 k n plus 1 minus h I j k n plus 1 over delta z I plus 1/2 j k minus ky I j minus 1/2 k h n plus 1 I j k j minus 1 k n plus 1 over delta y I j minus 1/2 k. All right, and then finally the z term. One over delta z I j k times k sub I j k plus 1/2 h n plus 1 I j k plus 1 minus h sub I j k n plus 1. Oh, I see a mistake here, sorry. This is not delta z up here, because we have here, oh, I messed this whole one up here. I j plus 1/2. Sorry, because down here we're going to have delta z I j k plus 1/2 minus k z I j k minus 1/2 h n plus 1 I j k minus h n plus 1 I j k minus 1 over delta z I j k minus 1/2. Okay, whew. It's a lot of I, j's, and k's, right? But it's really the same template, just repeated in each direction and over time. All right, so we can set this up as a system of equations. However, I'm going to do a little trick here. I'm going to multiply both sides. So if I multiply both sides by delta x I j k delta y I j k and delta z I j k, which this is really equal to the volume, right, of this cell. All right, so if I multiply both sides by that, what I'm going to end up here is with a new set of terms. Each one of these is going to now become an area, and that area is going to be the face of the cell normal to a given direction. So if I multiply this by delta x, delta y, delta z, the delta z's will cancel, and I'll have a face delta x by delta y, all right? And that is a face perpendicular to the z direction, all right? It's the area across which flow will occur in the z direction. So if I do that, I will get a series of equations. So if I do that, let's just look at this term here, right? If I multiply by delta x, delta y, delta z, so delta x, delta y, delta z over delta z, we'll all end up with delta x over delta y, which is a plane of area, and I'm going to call it a sub z because it's the area perpendicular to the z direction. All right. Now let's introduce a couple other terms. These are mod flow terms, all right? And we're going to call the conductance of a cell, C, is equal to K, the average hydraulic conductivity between two cells, times the area in the direction of flow, divided by the distance between the two cell centers, all right? So A is area perpendicular to flow, and L is the distance between cell centers, and K is the average K between cells. All right, so let's call, this is specific mod flow nomenclature, C sub R is equal to Kx, Ax, Lx. Cc is equal to Ky, Ay, Ly. And Cv is equal to Kz, Az over Lz. All right, so if I do the multiplication, all right, I multiply, so I do the multiplication by volume on both sides. I separate each term out, and I use these definitions here. I'm gonna define two more things here while we're at it. H cough is going to be the volume, all right, times the storage coefficient, so S sub S delta T, all right, and the right-hand side, RHS, is going to be V S sub S V H I J K N, current time step, over delta T. Okay, so if I apply these definitions, I do some multiplication, and I do some algebra, all right? And you can do this for yourself. I'm not gonna do all the algebra and steps, but if I do some rearranging, I get this equation. So I have CV I J K minus 1/2. All right, times H n plus 1 I J K minus 1 plus CR I minus 1/2 J K H n plus 1 I minus 1 J K plus CC I J minus 1 K H n plus 1 I J minus 1/2 K. Oh, sorry, this is 1/2 and this is 1 here. All right, plus, and I'm going to move this whole term down here. This is parentheses minus CV I J K minus 1/2 minus CR I minus 1/2 J K minus CC I J minus 1/2 K minus CV I J K plus 1/2 minus CR I plus 1/2 J K minus CC I J plus 1/2 K. Oh, sorry. Can't end the parentheses yet. Plus H cough I J K. All right, this whole parentheses, this whole term here is multiplied by H I J K to the n plus 1. All All right, so you can think about it this way. These are all the minus terms, all right, times hk minus 1 times hi minus 1 times hj minus 1. These are all the current location, all right, all the terms times the current location. All right, and then we're going to add in the plus 1 location. So we've got plus CV I j k plus 1/2 h I j k plus 1. I just gotta check something out here. Okay. Minus CR I plus 1/2 J K H N plus 1 I plus 1 J K plus CC I J K H N plus 1 I J plus 1 K. All right, and all of this stuff is equal to the right-hand side, RHS I J K. All right, so this whole thing, let's call this whole bracket term here, or parentheses term, this whole thing that we're multiplying by the current location. Let's just call it B. All right. Well, we can think of this now. We can write a system of equations, all right, where we've got this big bracket, all right, and we've got a bunch of diagonals. This one here, the main diagonal, this would have B's on it. All right, each one of these would be B. And then we'd have other diagonals. You know, this one, this diagonal here would be CV. This diagonal here would be CR. CC. CV. CR. CC. So these are all diagonals. All right. They are being multiplied first by this H n plus 1 vector. And so our first one would be here that we're looking at. We'd have dot, 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 CV times H, I, J, K minus 1. All right, CR is multiplied by this, so sometime H, I minus 1, J, K, and so on and so forth. All right, and these would be equal to the heads, the RHS, so this is SSH SS times V I J K H I J K at the N over delta T. All right, so we have this system of equations now. This would be our matrix A. This is our vector H n plus 1. And this is our vector SS V H n over delta T. All right, so the same set of equations that we had previously talked about. All right, we just have a different matrix. It's a little more complicated because it has 3 dimensions now. So there's 1, 2, 3, 4, 5, 6, 7 diagonals now, and they're not just right on the main diagonal like they were for our simpler system. All right, they're spaced out, but that is essentially what ModFlow's done. It's just done the exact same thing that you guys have already done with our simpler system. It has done a lot more bookkeeping. It's created a more complicated matrix, but it creates the same set of matrix equations, and then it uses a solver to solve for H n plus 1 is equal to A inverse times this RHS. All right. So that's what ModFlow does. That's the finite difference solution. It's much more complicated, but it's essentially the exact same thing, just allowing variable spacing and heterogeneous and anisotropy. All right, this will be a good place to stop here. And we'll see you guys again, talk about some other different methods of numerical solutions.